What's up, nerd gang? So I'm going to try to get through some of these a little bit faster. Almost done with the written response section of the August 2015 Chemistry Regents. So I'm going to start this off right away. We're on question number 75. Let's pick let's see. Let's go with purple. Sounds good to me. Cool. All right. 75 and 76. During the winter months, icy roads pose a threat to motorists and can lead to accidents. A mixture of sand and sodium chloride, NaCl, can be spread on roads to make winter driving safer. One New York town requires that a mixture of sand and salt used on residential roads should contain 25% or less sodium chloride by mass. So this is the mixture of sand and table salt. A 10-gram sample of a mixture of sand and sodium chloride was analyzed, and it has 3.3 grams of sodium chloride in the 10-gram total sample. Okay. First problem. Number 75. State in terms of freezing point why sodium chloride is part of the mixture that is put on icy roads. Okay. So you've probably noticed this in your life. Every winter, we put salt on areas that get a lot of snow and ice. The reason why is because the more of a substance that is not water that is dissolved in water, what this does is it lowers the freezing point. So let me see if I can maybe make some sense out of this. Let's see. So, and I can't draw so well, but let's see. So if we think about it, so you have a water molecule, right? So let's see. Hey, where'd you go? Said we have a water molecule. Okay, so you have oxygen, hydrogen, hydrogen, right? So there's a water molecule. And here's another water molecule. Hydrogen, oxygen, hydrogen. And another water molecule over here. Oxygen. Oh, by the way, hydrogen bonding. The hydrogen and oxygen are very attracted to each other on different water molecules. So basically what I'm trying to show you is that for water molecules to attach to each other and form an ice crystal, the hydrogen on one atom has to face the oxygen atom. The hydrogen atom on one water molecule has to be facing the oxygen atom on another water molecule, and they attract each other over and over and over again until you end up with snowflakes, like ice crystals. The thing is, if you add sugar or salt or any other substance, here, let's pick a different color. So let's say you add salt to the water. The salt particles will get dissolved by the water, meaning that instead of the water molecules focusing on sticking to each other, they'll stick to a salt molecule. And this water molecule will attract to another salt molecule instead of the other water molecule. Long story short is that the water molecules, instead of being attracted to each other so that they can make an ice crystal, they're sticking to whatever you dissolved in, whatever solute. This means that the water molecules don't attract to each other enough to make an ice crystal, meaning no ice. So the more of a substance that is dissolved in water, the lower the freezing point gets. So a higher concentration of solute dissolved, a higher concentration of dissolved solute, which is whatever you dissolve, will lower the freezing point. This is called freezing point depression. And no, it doesn't mean that the water is sad after you put salt in it. We'll lower the freezing point. Okay, and there's something else that happens while we're at it. Not only does adding more of a solute to water lower the freezing point, think about if you have a container of water. Here, let me draw some water. So here's plain water. Okay, now you got to think the top layer here is water molecules. And if they want to, shake and vibrate enough so that they escape and evaporate as a gas, they can. But if you have solute particles like salt or sugar, the more particles that you dissolve in the water, that means that floating on the top of the water are the solute particles, not just water molecules. So this is kind of like, imagine the water molecules down below, they cannot evaporate because there are other solute particles in their way. They can't evaporate out. Not only that, some of the molecules and atoms and ions on the top layer are not water, so they won't evaporate. What this means is that the more solute that you have dissolved, not only does it lower the freezing point, but it raises the boiling point. This is called boiling point elevation. And if you're careful, you could try this at home with a thermometer. Take plain water, put ice in it, measure the ice water. Boiling water, we know, should be 100 degrees Celsius, 212 Fahrenheit. If you have ice water with salt in it, the temperature will drop more than the normal freezing point for water. And if you have salty water, the boiling point goes above 100 degrees. And the more stuff you have dissolved, the more this happens. So now let's answer the question. Why is sodium chloride put on icy roads? That's because dissolved NaCl will lower the freezing point. And this means you don't get ice, or not as easily. And don't forget, when we say freezing point, we really mean the freezing temperature. So the water will not freeze solid unless it gets even colder than normal. So the more substance is dissolved, the lower the freezing point, which means you do not get frozen ice as easily. Okay, next question. Explain in terms of composition by mass why the mixture from which the analyzed sample was taken should not be used on residential roads. Okay, go back to the reading with me. This town says that the amount of sodium chloride put on the ground to stop ice from forming should only be 25% maximum or less sodium chloride by mass. This analysis showed that 10 grams of the mixture had 3.3 grams of sodium chloride. So what we want to do here is use the equation for percentage error. If you look at the equation for percentage error, it's pretty easy. Not percentage error. Percent composition. Percent composition by mass. You take the mass of the part you're analyzing divided by the total, the whole mass, and it's a percent, so we multiply by 100. So if we try to work that out based on this info, it says that there were 3.3 grams of sodium chloride out of a 10-gram sample. So if we do a quick calculation of that, that's 3.3 grams divided by 10 times 100. That's not 25% or less sodium chloride, that's 33%, meaning that is too much than the town wanted. The reason why they might not want so much salt is because salt will actually damage, well, we know that it rusts metals and it also injures cars. That's the thing. The salt on the roads will injure, or rather, it will rust and oxidize car parts. Salt crystals forming in the roads can actually make the roads crack even more than the ice. So anyway, 33% composition by mass is too high. So that's it. So let's write that. So the sample contains 33% NaCl by mass, not 25% or less. So it's too much salt. All right. Not bad. Let's go to the next two problems. Right. I'll leave those there for now. 77 and 78. In a laboratory investigation, different color now. I'll use purple still. In a laboratory investigation, a solution, so a homogeneous mixture, that contains 13.2 grams of, this is lead positive 2 nitrate, reacts completely with a solution that has 12.0 grams of sodium iodide. And this reaction produces 18.4 grams of lead positive 2 iodide and an undetermined mass of a second product, sodium nitrate. This reaction is represented by the balanced equation below. Hey, that's nice. At least they gave us a balanced equation. So here we go. Lead 2 nitrate reacts with, well, let's think. There's an invisible 1 in the front. So there's 1 mole of lead nitrate lead 2 nitrate, reacts with 2 moles of sodium iodide, and this produces 1 mole of lead iodide and 2 moles of sodium nitrate. Do you recognize this type of equation, by the way? A with X, B with Y, and we have A with Y and B with X. This is a double replacement reaction. I don't know if they asked us about that, but still, you should know that. This is a double replacement reaction. How do we know there was a double replacement reaction? Well, because of the answer for number 77. It says, identify the compound produced that is insoluble in water. So we have to identify either lead iodide or sodium nitrate as insoluble in water. The reference table we have to use is reference table F. So let's go to reference table F. So reference table F shows us which aqueous compounds will dissolve in water or will not dissolve in the water. So it'd be nice if I could actually get to table F at some point. Okay, let's see. Nope, past it. Here we go. So if you're looking at table F with me, check the 2 columns. I'll make a few notes. The column on the left says that these are ions that form soluble compounds, which means the exceptions would be the opposite. So those would be insoluble. And on the right side, this column says these ions usually are insoluble, which means these exceptions would be able to dissolve in water, so soluble. So let's check those products. We have PbI2, so lead 2 iodide, and we have sodium nitrate. Well, what about this? Check this out. So if you look at this column right here, it says sodium and all the group 1 metals are soluble with no exception. That means that sodium and all the other metals in group 1, they make salts that dissolve in water all the time. So then, we already know then that this is not what didn't dissolve. Sodium nitrate is soluble. They want us to find what is insoluble. So we could check lead with iodide. So I don't see lead anywhere, but I do see iodide rather, the negative ion. And iodide is usually soluble, but not with lead, which means lead iodide is insoluble. There we go. That's the insoluble product, is PbI2, lead positive 2 iodide. That's the answer. Okay, and now they want us to determine the mass of sodium nitrate produced. So in order to answer this, we're going to have to use the balanced equation, but shouldn't be a big deal. So I'm actually going to clean up this page so we could see a little bit better. Actually, no, should be fine. Let's see. So they want us to determine the mass of sodium nitrate produced. So here's the deal. We can choose either one of these reactants, the lead nitrate or the sodium iodide. We could choose the amount, the mass of either one of those that was used at the beginning to calculate this. I will go ahead and I'll just choose the sodium iodide, NaI. And also, I'm going to clean this up. It's hard to see what I'm doing right now. So delete everything. There we go. Okay, let's try this again. So I'm going to look at this just for the heck of it, because that's what they gave me. So we know that we started with 12.0 grams of sodium iodide. So we're going to start with that. Now, because we're going to be using some fractions that we're going to multiply by, it makes me feel more comfortable to put a number that's by itself. I'm going to put it over 1, just because it looks like a fraction now. Okay, and I believe the next thing that we're going to have to do is figure out the formula mass of sodium iodide. Oh, no, actually. We're going to have to figure out the mass of sodium nitrate. Or both. Okay, I'm going to do both. All right, so on the side here, let's find the mass of sodium iodide. So we have 1 sodium and 1 iodine. So let's check the periodic table. I'm going to clear all this. Check the mass of those elements. So if you need to find the molar mass or the gram formula mass, we're going to have to check the mass of these elements. So I'm going to go to the periodic table. and find the mass of sodium and iodine. Okay. So the mass of sodium, Na, this would load, that would be really nice. Okay, taking forever. Well, while that's loading, I'm going to keep it moving. Sodium has a mass of 23. Okay. And oh, look there, finally, 22.989. So just round this mass of sodium to 23. Let's check iodine, much heavier element. Iodine's mass is about 126.9, so 127. 127. So if we add those two together, we got 127 plus 23. The mass of sodium iodide is 150 grams per mole. Okay, so then that means that if we use the equation, the number of moles is equal to the given mass divided by the formula mass, which is also on table T. It's on the reference table. That means to figure out how many moles of NaI, sodium iodide, we have 12 grams divided by 150. It's 12 divided by 150. 0.08 moles. 0.08 moles. Okay. So let's see. Oh, and I actually could have done that within here. So I could have said the number of moles of sodium iodide is, you would find that by dividing by 150 grams. Okay. Continuing. So now we've got two fractions, but we have to keep going because they want us to find the mass of sodium nitrate produced. So now we're going to have to use the equation. So if you look, we're looking at sodium iodide and sodium nitrate. So something here is going to make our lives easy right now, which is the fact that if you look at the coefficient in front of those the two substances, two compounds, you see that it's 2 moles of sodium nitrate corresponds to 2 moles of sodium iodide, which basically means it's a 1-to-1 ratio, right? 2 to 2 is 1-to-1. It's kind of like a cooking recipe. Okay. And now the last part that we have to do is, and I could show you that we're on our way, is that we have grams of sodium iodide and grams of sodium iodide. That cancels. We have moles of sodium iodide gone. Now we have moles of NaNO3, which is sodium nitrate. We're almost there. We just need to turn that to mass. So we're going to do the same thing we did with sodium iodide. We're going to do that with the elements sodium, nitrogen, and oxygen in sodium nitrate. So I'm going to do this. I'll do it in a separate spot to make it a little bit cleaner. So I'm going to delete all this. Okay. So stick with me on this. Almost done. So let's see. The formula is NaNO3. Okay. So sodium nitrate. All right. So we have a sodium, nitrogen, and we have 3 oxygens. So let's go back to the periodic table. Sodium's mass is 22.9, so that's about 23. Oops. So that's only 1, so that's 23. Nitrogen, there's only 1 nitrogen atom there, so nitrogen's mass is about 14. And oxygen, there's 3 oxygens, so I'm going to say 3 times, and the mass of oxygen is approximately 16. So 3 times 16. That's 48. Okay, so if we add all of those together, 23 plus 14 plus 48. 23 plus 14 plus 48. 85 grams per mole. So 85 grams per mole. Don't let all the science confuse you. This is similar to saying, a box of 12 apples weighs 5 pounds. It's like 5 pounds per dozen, right? 85 grams per mole. So instead of talking about apples in a dozen, we're talking about grams in a mole. So very similar. Okay, so let's go back to that. So the mass of sodium nitrate is 85 grams per mole. So we're going to multiply that. It's 85 grams of sodium nitrate per 1 mole of sodium nitrate. Okay, let's see. Grams cancels out. Moles of sodium iodide cancels out. Moles of sodium nitrate cancels out. And we're left with grams of sodium nitrate. Cool. Now all we have to do is, well, some math. We just multiply across the top of the fraction and across the bottom and divide if necessary. So let's see. The top is going to be 12 times 1 times 2 times 85. 12 times 1 times 2 times 85. Okay, now divided by 150 times 2. So divided by 150 divided by 2. There we go. The amount of sodium nitrate produced is 6.8 grams. So the answer is 6.8 grams of sodium nitrate were produced. I know that these mole calculation problems seem like a lot. I might even make a separate video showing you how to work on those. That I'll focus on that only, okay? All right, I think that's good for this video. Look back over that one if you got a little lost, but it's not that bad.